intermittency or intermittent dynamics in logistic map, and I will present it in its relation to three periodic solutions. So we consider logistic map again. Un plus 1 equals r un 1 minus un. So u naught is in the segment 0, 1, and parameter r is positive but doesn't exceed 4. So we know that here we have at least one period doubling cascade. In fact, we have infinitely many period doubling cascades here. But first one is taking place for transition from fixed point to periodic solutions, for periodic or 2 to the power of 2 periodic, and 2 to the power of infinite periodic. So this fixed point here we will consider U2, from which two periodic solutions give rise, and this occurs when r equals to 1. Then two periodic solutions occur when r equals to 3, and so on, and 2 to the power of infinite when r approximately equals to 3.5699 and so on. So it is 5, 6 and so on. And what I claimed in one of my previous lectures, that we in logistic map we can also have solutions of other periodicities. And today we will be mostly talking about three periodic solutions. So three periodic solutions for logistic map appear to be fixed points for three terate map. So for this x n plus 1 equals to f3 of xn, where f is logistic map. Again, so this is f3 is polynomial of 8th degree. And it can have up to 8 roots. So what happens here, first two roots are fixed points of logistic map. But with extra 6 other roots exist, real. When parameter r is more or equal to 1 plus square root of 8. So I didn't prove it. It is a very long way to prove it. It is known. And they appear at the same time. So these 6 roots, they form 2 triples. 6 roots form 2 triples. And here on this figure, there is illustration of these roots. So here we have f3 of x. This is 3 composite map. So then these red points, 1, 2, and here is red, 3, So this 1, 2, 3 is one 3-periodic solution. And we have also 4, 5, here, 6, 4, 5, 6. It is another second 3-periodic solution. So what is important here? They appear at the same time, at the same value of r, which is 1 plus square root of 8. One of them is stable and another is not. This one is stable, which is represented by reds, and this is unstable. And then what happens later on, this red one, when r is increasing, this red one also becomes unstable. So this becomes unstable later. Becomes unstable when r is increasing. But second one is always stable. So this is certain information about 3-periodic solutions. And now here some kind of illustrations. So here we have r very close. Let's say it's 1 plus square root of 8, just slightly less than this, minus epsilon. This is r less than 1 plus square root of 8. I think here it was 3.8. And here r is more than 1 plus square root of 8. I think it was 3.835 or something like this. I don't remember. So here we have 3-periodic solutions. Here we don't have. So here we don't have 3-periodic solutions. And when we don't have periodic solutions, when r is less than 1 plus square root of 8, we have chaos. When r is more than 1 plus square root of 8, well, not significantly more, but just a bit more, then we have 3-periodic solutions. And transitions from chaos to 3 periods takes place through so-called intermittent dynamics. So this is intermittency. See what we have here. We have this band, 3-periodic solution. This band is 3-periodic. And here we have chaos. So this is a switch. We have a switch. 3-periodic chaos and again 3-periodics and again chaos. And this takes place because at this place, and this place are function f3 very close to diagonal line. So this is illustrated here. So this piece here is we can say it is like some piece here. This piece. To explain intermittency regime, I will consider this image, and this image in fact is this red image in the middle. So this is just a small part of f3 function. So what we can see here, assume x naught is here, x naught is 0.5. Then it will take quite a while, there will be many iterations before it gets here. Say x m is 0.55. So here there will be many iterations. And what eventually happens, this, what we have here, is three-periodic solution. And outside here, chaos. To explain it, I will draw Fn. Let's say xn plus 1. This is our f of x. You remember this was part of f3. Now, this is diagonal line. This is y equal to f of x. Assume we started somewhere here. This is, say, x naught. Then this will be x1. Then this will be x2. And we can see that this will be, so function at f2 of x2 is x naught. Let's put it like this. x1 is f of x naught. x2 is f of x1. And x naught is f of x2. And this x naught, x1, x2 here is correspond to this point. This is x naught, x1, and x2. So these are fixed points of f3 map. So this is three-periodic solution. And this is only one of them. Let's say here we have this here, something like x2. So it's x2, then x5, then x8, and so on. Something like this. So here we have only one of these values, and they repeated. So they every third time you will get the same value. So our task now is to estimate how many iterations it takes to pass this narrow corridor and to change value of x from 0.5 to 0.55. So what we want to do, we want to estimate number of iterations for passing the narrow corridor. Which is in fact size of three periodic bands in intermittent solution. So I will plot again, even in a smaller scale, what we had. So this was x, this was y, this is diagonal line, and this is our function f. So what we want to do, let's find point here. I will call it x capital. And at x capital, the vertical distance between f of x and y equal to x is shortest. So this distance I will call it epsilon, shortest distance. So what we can say, we can put like this: f at x capital will be equal to x capital plus epsilon. So what we can say even more, derivative of f at x capital should be equal to 1, because tangential to our line here should be parallel. Tangential should be parallel to diagonal line. Tangential is parallel to diagonal line. So if it's not parallel, then at this point, distance between y equal to f of x and y equal to x wouldn't be shortest. Yeah. So assume. So I take it you understand why it should be equal to 1. Then we can write now. So we find second order approximation of f of x, and taking its Taylor expansion at x capital. Plus half second derivative at x capital times x minus x capital squared. Now f of x equals, we remember that f at x capital was x capital plus epsilon. We remember that derivative of f at x capital was equal to 1. And here we don't know second derivative, but half second derivative we will just denote by something like a. So a is half of second derivative of x at x capital. So second derivative of f at x capital. So a times x minus x capital squared. So this will be equal to this x capital and this x capital cancel each other. We will have x plus epsilon plus a times x minus x capital squared. Thus, approximation of our map xn plus 1 is equal to xn plus epsilon plus a times xn minus x capital squared. Now we will use the following trick. We take xn to the left hand side. This at one hand should be equal to epsilon times a xn minus x capital squared. On the other hand, we will use this trick xn plus 1 minus xn. We represent it as xn plus 1 minus xn divided by n plus 1 minus n, which is divided by 1. And here we have change of x at n step, and here is change in number of steps. And this we will replace by derivative dx over dn. So now n is considered to be continuous variable. It is like swapping between difference equation and differential equation. So what we got is dx over dn equals to epsilon plus a times x minus x capital squared. So after separation of variables, we will have dx over epsilon plus a times x minus x capital squared, and this equals to dn. What we want to do, we want to integrate this. Integral on the left hand side, on the right hand side, will give number of iterations for x to change from, let's say, x minus to x plus. X minus value on the left of the corridor and x plus on the right. So this integral is number of iterations, it's size of our three periodic band, and this integral is integral which you learned in Math 101. So this is, you can find it in table of integrals. This is arctan. So this is 1 over square root of a times epsilon arctangent x minus x capital times square root of a over epsilon, and this should be found at values x plus and x minus, which are limits of integral, and then it will be size of three periodic band. And this integral can be estimated. Let's check it. So this is x, this is n, so n is function of x. Let's say this is x capital. Now arctangent will look like this. So this limit is pi over 2 times square root of a epsilon. This limit is minus pi over 2 times square root of a epsilon. Let's say this is x minus and this is x plus. Then this is our value of function for x minus, this is value of a function of x plus, and this distance is n capital. Now, to estimate it, we can say, okay, so generally x minus and x plus, all x's should be between 0 and 1, remember this. But we can estimate this n. Well, it is less, not too much less, from distance between pi over 2 times square root of a epsilon minus pi over 2 times square root of a epsilon. So this is pi over square root of a times epsilon. Well, basically this would be, this is the value of integral. When x minus equals to minus infinity and x plus equals to plus infinity. But when epsilon is small, there is difference between this pi over square root of a epsilon minus n minus our integral is small. And finally, our final conclusion is that n is proportional to epsilon to the power of minus half, which means that if epsilon is, let's say, 0.01, then n is around 10. If epsilon is 10 to minus 4, then n is 100, and so on. So this is size of our three periodic band, and this is how close our function to diagonal line at these 3 points.